Let's talk about the friction lab on the horizontal plane. Let's start with the block at rest on the horizontal plane. What are all the forces acting on it? Of course, we have the weight going down. The block does not fall, so there must be a normal force holding it up. We're not pulling on it, so there's no friction needed to keep it in place. But if I pull to the right and the block does not move, there's an equal force of friction going the other way. The velocity is 0, so we call this static friction with the S. When I pull harder, the static force of friction increases until we reach the maximum static friction and the block starts to jump forward. We put weights on top and repeated the experiment. We collected data. We measured the normal force by weighing everything. And then we knew what the force of friction static maximum was by looking at the spring scale just when the block jumped forward. We made a graph of the maximum static friction versus the normal force. We got data that sort of looked like this. We drew the best fit line all the way back to the origin, because if you could imagine, if this thing had no weight on it at all, it would be just floating there and it would have no ability to generate any friction. The slope of this line has meaning. Since 0, 0 is on the line, we can simply say that the force of friction maximum divided by the normal force is the slope, which we call mu. That's a Greek letter. It's not an M, it's not a U, it's a mu. And because we're dealing with static friction, we put an S as a subscript to represent that it is static coefficient of friction. You probably don't recognize this as a coefficient. But if I rearrange the equation to look like this, yes, that's the coefficient, and you might recognize this as y equals mx. Well, plus b, that's 0. This is a linear equation. In the next part of the lab, we try to get the block to move at a constant velocity. Now we had to pull, but we could give it a little tap just to break that static friction and get it moving. We would adjust the spring scale and get this thing to inch along so slowly, the force did not accelerate the block, it moved it at a constant velocity. There's a friction force going backwards. That friction force, because we're moving, is called kinetic friction. How do I know what the value of the kinetic friction is? Well, when I get the block to move at a constant velocity, the amount of force I'm pulling with equals the force of friction kinetic. If I pulled harder than that force, it would accelerate. If I pulled less hard, it would slow down. So to maintain constant velocity, that force has to equal the force of friction. Well, we did this for different weights on top, and we changed the normal force again. We repeated the experiment and we collected data on the force of friction kinetic versus the normal force. And the data went off like this. It was fairly linear. There's a little bit of error in all of this data, and the best fit line would make the most sense to average out the error. Never connect these dots with a squiggly line or straight line segments, because then you're just plotting the error. And once again, you can imagine that if we wanted to keep this thing moving at a slow, constant speed, if there is no weight involved at all, there'd be no normal force, we'd have no friction. It would just be floating on the surface. Again, the slope of this line has meaning. The force of friction kinetic divided by the normal force would give us that slope because 0, 0 is on this line. And this is another coefficient of friction. But because we're talking about kinetic friction, we put the subscript k here. Now we notice that this coefficient of kinetic friction is lower than the coefficient of static friction. Well, you probably noticed that when you were doing the experiment and you pulled, and it lurched forward when the static friction was broken and it turned into kinetic friction. You notice that when you do this with moving a big box. If the box is on the floor, it feels stuck, you push, and all of a sudden it breaks free. Well, what's going on has to do with a microscopic view at the surface. If we zoom in on a surface, we can see that the box has undulations in them, and so does the floor. Well, these teeth, if you will settle in place and latch onto each other in such a way that they don't want to move when it's static. And then we push and push, and it pushes back. We push harder, it pushes back, until all of a sudden the teeth jump out of the grooves and they start to bounce along. Now, it's a little like having a bicycle chain and the bicycle gears are engaged. And if the chain slips, all of a sudden you lose your grip. And that's what's going on, why the kinetic friction is less than the static friction. Let's take a look at the meaning of mu. First, let's look at the units. Does this number have any units? It's newtons over newtons. They cancel out. Well, that would have to work that way because this is going to be a normal force, which is in newtons, and the force of friction is in newtons. So that can't have any units. Let's imagine we do the experiment again. We put the weights on top. We change the normal force, keep pulling just to get this thing started. And we get our data and draw the best fit line. Well, now I'm going to come along and spray it with a lubricating spray. And now we'll see what happens. For each trial, I won't have to pull as hard because I have the lubricating spray. That means my maximum static friction would be less for a given normal force. What does that tell me about the mu? The slope is the mu, and because it's so steep, it would tell me that it's rough. Because it takes less force to move the block, this has a lower coefficient of static friction, and we would say that this surface was smooth. So we can say that mu is a measure of surface roughness. Let's develop a problem. We have a 5 Newton block sitting on a surface. We're pulling with 2 newtons, and it remains at rest. Find the force of friction. Well, if it's not moving anywhere, the sum of the forces has to be 0. So it must be 2 newtons going the other way. What type of friction is this? If it's not moving, we say it's static friction. Could you calculate mu(s) with this data? You know the weight, you know the normal force, you know a force of friction. We could just use this equation and calculate mu(s). But we're getting sloppy. That is not just any old force of friction. It has to be the static maximum, and we don't know if we've reached the static maximum yet in this problem. I haven't gotten it to start moving yet. So I pull harder. The block doesn't move yet. My force of friction goes up to 3 newtons. I still haven't moved yet, so I need to pull a little harder. Just as I get to 3.5 newtons, my friction has increased to 3.5 newtons, but suddenly it gives way and the block jumps forward. That's when I know I've reached the maximum. Now I can calculate the coefficient of static friction. I get 0.7, no units. Now that the block has jumped forward, imagine I keep applying that 3.5 newtons. The block will speed up. I know then that this force of friction has to be less than the 3.5 newtons. Since it's moving, we put the K here to call it kinetic friction, but I don't know what that number is. I'm going to reduce my force to 2.5 newtons, and when that occurs, I notice that the block is moving at a constant velocity. Now, under these conditions, we can now find the force of friction. That force has to be equal to this one. Now, could we use this information to calculate the mu K? Yeah, we know what that force is, and we have a mu K of 0.5. Now, keep in mind that this is only a 1 data point calculation. In our lab, we did this over a number of normal forces and found the best fit line. This is theoretically going to be okay if we assume these numbers are correct. But in a laboratory situation, you wouldn't want to trust just one measurement to get your mu. Well, let's reset the block at 0 and put a little weight on top, 3 newtons. The mu is still the same because it's the same surface. Find the force pull needed to start moving the block. Well, the weight of the block is 5 newtons, but now we have 3 newtons pushing down on this surface as well through the block. Well, it's like having an 8 Newton block. The normal force will have to be 8 newtons. We'll find the maximum static friction. You'll take the coefficient of static friction multiplied by the 8 newtons for the normal force. Well, we get 5.6 newtons for our maximum static friction. Well, now the question is, how hard would I have to pull? Well, I'll have to pull at least this hard, 5.6 newtons. You see, this is just a threshold. If I pull a little less, it doesn't move. If I pull a little more, it's going to move. Now imagine we have the block in motion with this extra weight on it, and we want to find how hard we have to pull to maintain constant velocity. Well, if I pull this hard and this force has been broken and it turns into kinetic friction, that will be smaller than that force and the block will speed up. So therefore, we will reduce how hard we pull. You can just take the mu kinetic times the normal force and get the force of friction kinetic. That force of friction kinetic goes right here, which means we're going to pull with a force of 4 newtons. Okay, so let's make a quick summary so far. We're dealing with static friction when the velocity is 0. The force of friction static on an object rises from 0 as we push on the object up to some force of friction static maximum. So the force of friction static could be any number from 0 up to the maximum. And this is the force of friction static maximum, which can be calculated from how rough the surface is times the force that the block and the surface are pressed against each other. And then we have kinetic friction for any time the block is moving. The kinetic friction is a constant value. Whether we're moving fast, we're moving slow, we're speeding up, we're slowing down, once the block starts to move, the model we're using assumes that the force of friction kinetic is constant. The teeth that I was talking about, how the surfaces lock into place, that's how we generate a changing static friction. It all depends on how hard we push against it. But once they start to bounce across the tops, as they fly across there, you're going to have a constant value, whether you're speeding up, slowing down, or moving at a constant velocity. Now, in real life, the model is more complicated than that. But this is how we're getting started with friction. And that's the formula we're using to calculate the force of friction kinetic. Well, let's try another problem or two. I take a block, I place it on a plane. Initially, it's 0 velocity. I'm pulling with 5 newtons, and here are my coefficients of friction, static and kinetic. Well, we can ask, what is the current force of friction? First thing a kid is going to say is it moving? Well, not initially. Why don't we find out what the maximum static friction is? We write the formula, put in our values, and we get 6.75 newtons. A common mistake now is for kids to say, oh, that's the current force of friction. No, it's not. If that was the amount of friction we'd have, and this thing started out at rest and I'm only pulling with 5 newtons, it's going to take off and go backwards. Well, nobody puts a block on the table, pulls forward on it, and has the thing shoot backwards. That's impossible. So that's the maximum friction we can get. What is the current force of friction? It's 5 newtons. And it's static, just not the maximum. It's only going to be as big as hard as we're pulling. We haven't overcome static friction. Now imagine while I'm pulling with 5 newtons, I give the block a brief tap to move it forward. That tap helps me break static friction, but then I no longer push on it. So I've set the block in motion forward. My pull still remains at 5 newtons. What will the block do? Your choices are, it could move at a constant velocity. It could speed up. It could slow down. That all depends on the force of friction kinetic. So we'll answer this question again. What is the current force of friction? If it's moving, it's got to be kinetic. There's the formula. We get 3.75 newtons. We put it on the diagram, and we compare it to how hard I'm pulling. They're not equal. That's bigger than that. It's going to make it speed up. And that's the answer. Now, again, you might be saying, but doesn't that depend on how fast we're going? In real life, yeah, that's going to matter. But for our simple initiation into friction, we are assuming that this model tells us that that friction stays the same. As long as we're moving, that's the value you're using. And now for something a little more tricky. Let's assume this block is moving at a constant velocity to the right. This force is acting on it at a 25-degree angle, and it weighs 30 newtons. Find the force of friction. Well, any kid doing physics is going to see this and say, we better make components. I get 10.9 newtons for the x component and 5.07 newtons for the y component. Let's complete the free body diagram. We have a 30 Newton weight, and we have to have a normal force. How big is that normal force? A lot of kids would say, right off the bat, it's 30 newtons. We have 30 newtons down, have 30 newtons going up. But not so fast. We have a y component from this force acting up. We saw this with the water bottle on the spring scale and the electronic balance. The total forces up have to equal this force going down. So we have 24.93 newtons for the normal force. And of course, since we have a velocity going to the right, there must be friction going to the left. And it's kinetic. And since we're moving at a constant velocity, we know the force going forward must be equal to the force going backwards. And there we have it. We know the force of friction. Now we could even find UK for this problem if we wanted to. We would take the force of friction kinetic and divide by the normal force. And this is where kids really screw up. They put the 30 in here. It's 24.93. And I get 0.44. Well, in our next lab, we'll be doing this all again on an inclined plane. In the meantime, you can read the chapter notes on friction in section 3.2. Do the worksheets on friction, and then go and check the answer keys that I send out. Good luck.